Alright, welcome once again. So today we want to look at gas power cycle. Is that under that we'll be looking at Carnot cycle and Otto cycle. So to start with, for a Carnot cycle, so on the screen we have two charts, as in two diagrams. We have the PV diagram and the TS diagram. For the PV diagram, it illustrates pressure against volume, and for the TS diagram, it illustrates what's it called, temperature against entropy. You understand now? So what is a Carnot cycle? A Carnot cycle is an ideal heat engine. Is that taken? Or basically it is a theoretical thermodynamic cycle which was proposed by Sadi Carnot. Sadi Carnot was a French engineer in 1824. So the cycle works on reversible cycles known as constant temperature. Is that taken? It means that what heat is being added at constant temperature and heat is being removed or rejected at constant temperature. If you consider the the TS diagram, which is temperature against entropy, you can see that this process 1 to 2, it is heat received or added. You can see at constant temperature, that is isothermal. It simply means that process 1 to 2, so process 1 to 2 is isothermal. Is that taken? This is how isothermal looks. 1 to 2 isothermal. So at constant temperature. Is that taken? Now process 2 to 3, it is adiabatic expansion. It expands. Adiabatic expansion. This is adiabatic expansion. On PV diagram, this is how it looks. Now if you are plotting it on TS diagram, it will be a vertical straight line. Look at it. Adiabatic expansion. So it comes down. Is that taken? Now the next process, process 2 to 3 is adiabatic expansion. Now process 3 to 4, yes, it is heat rejected at constant temperature, which is T3. You can see T3 is equals to T4. You understand now? So this one is heat rejected, which is heat received. Now this one is isothermal. This is also an isothermal, which is heat rejected. Okay. Now the next process, which is 4 to 1, look at it. It is adiabatic compression. Adiabatic compression. Is that taken? Now let us consider this TS diagram. You can see that your T1 is equals to your T2. T1 is equals to T2. T4 is equals to T3. Also, this is the entropy. Your S1 is equals to S4. Your S2 is equals to S3. Can you see that? Now, what is now the efficiency of a Carnot cycle? Efficiency, we call it thermal efficiency. Thermal efficiency of a Carnot cycle is this, is equals to heat received minus heat rejected over heat received. So what's the formula for our heat received? For our heat received, where do we have heat received? It is process 1 to 2. Is that okay? So for process 1 to 2, we have what? Heat received. So which will be given as T1 into brackets. Now does the line span, that is S2 minus S1. I'll say S2 minus S1. For heat rejected, it is, I can call it T3. Is that taken? That is S3 minus S4. That's it. So here I will now substitute. This one is heat received. That is T1 S2 minus S1 minus T3, that is S3 minus S4 over T over T3, which is heat received, that is T1 S2 minus S1. If I want to split this equation now, that is thermal efficiency T1, that is S2 minus S1 over T1 into bracket S2 minus S1 minus T3 over T1. Then I'll have my S3 minus S4, then S2 minus S1. Okay, you agree with me that this will cancel this. I have thermal efficiency is equals to T1 over T1. This one 2 goes, so I'll only have 1 there. Okay, this is 1 minus, okay, then here I have T3 over T1. Now here, what is this now? You can see S3 is the same thing as what? S2. If I'm to put it S2, this one is equals to S2, as in my S3 is the same thing as S2. Then I'm substituting S2 there, minus, what is S4? S4 is the same thing as S1. You can see on the screen, it's equals to S1. So S1, so then we have S2 minus S1. It will cancel each other. Then I have this now. This is now the formula for thermal efficiency. Is that taken for a Carnot cycle, where this T3, the T3 is known as temperature of source, temperature of the source. Now T1 is the temperature of the sink. Is that taken? So for you to have higher efficiency for the thermal, what's it called, for the Carnot cycle, is that taken, your T1 must be greater than T3. So it simply means that the higher the T1, the higher the sink temperature, the more the efficiency. The more the efficiency. That's all about thermal efficiency. Don't forget your T3 is the what? Is the temperature of the source, then T1 is the temperature of the sink. Is that it? Now the next one we want to consider is Otto cycle. What is an Otto cycle? Is that again? Okay, but before that, yes, we have what's it called? Air standard cycle. Yes, that reminds me. Air standard cycle. Air standard cycle. So what is air standard cycle? An air standard cycle is a cycle that uses air as the working fluid. It uses what? Air as the working fluid. Let's take for example now. You know, you have your refrigeration and air conditioning. The working fluid there is the refrigerant. Although there are so many types of refrigerant, is that again? So it's just the application of it now. Now this one is air standard what? Cycle. The working fluid is what? Is air. Is that it? Like your car? You understand now? Air is part of what makes the combustion to take place. It's part of it. You understand now? So for air standard cycle, the thermal efficiency is just 1 minus T2 over T1. It's the same thing. This one is the source and this one is the sink. That's just it. Now let's quickly go to Otto cycle, because this is the most interesting part of, is one of the most, or is one of the interesting part of thermodynamics when it comes to this aspect. You understand? So for this one now, we have PV diagram and we have what? The TS diagram as well. We have the TS diagram. Okay. So for the PV diagram, here from process 1 to 2, is that this is adiabatic compression. Adiabatic compression. Is that taken? So this is just its twin brother here. 3, 4. Is that taken? For an adiabatic compression on a PV diagram, this is how it goes. Then you are going to have a vertical straight line on the TS diagram. So if the heat is compression, the arrow will go up here, of which the arrow is going towards the side also. That's how to plot graph, because for every question you solve, you are expected to have an illustrative graph to tell the examiner or the person that wants to mark that, okay, this is what you are trying to explain. You get? So this is it. Now here, this is where process 2 to 3, this is heat added at constant volume. It is being added at constant volume here. Constant volume. You understand now? It is added at constant volume. So, and the process which we have it added at constant volume, it is isochronic. So here it is added at constant volume. So here CV, it is it added at constant volume. So here now, so this one is what? Adiabatic expansion. Then when it comes like this from 3 to 4 is adiabatic expansion. Then this one is what? It's rejected at constant volume. So Otto cycle works on the principle of constant volume. It is added and rejected at constant volume. That's what you have to know about Otto cycle. So there are 4 processes there. Adiabatic compression, which is from process 1 to 3. You can label it any number. You start taking for process 1 to 2. That is adiabatic compression. Is that taken from process 2 to 3? That is heat added. Heat added at constant volume. Is that taken? You can see. Now from process 3 to 4, this is adiabatic expansion. Adiabatic expansion. Now, which is 4 to 1 now, is now what? It's rejected at constant volume. It's rejected at constant volume. Is that okay? Now for every aspect, which is process 1 to 3, let us now derive the formulas. So for adiabatic compression, which is process 1 to 2, what really happens for process 1 to 2? But before we move on, we have what we call swept volume here, and we have clearance volume. The clearance volume is your V2. Is that okay? Your swept volume is now V1 minus V2. Now total volume is just your what? Your V1. Total volume is your V1. So, and the ratio of V1 to V2, as in your total volume to swept volume, that's what we call compression ratio. It's called compression ratio. Compression ratio. Compression ratio. It's as simple as that. Okay, now we want to consider each processes now. Each process. But before then, okay. But before we move on to the process, let us quickly look at the efficiency of Otto cycle. For Otto, is that taken? You know that efficiency is equals to heat added minus heat rejected over heat added. What process do we have heat addition? It was added at constant volume here, that is from here to here. Is that okay? So the temperature is the temperature that is changing now. Is that okay? The temperature changes from T2 to T3. So this one we are going to, and this is where So sorry, for this now, this is where heat is added and the temperature changes from T2 to T3. So T3 is greater. So now be CV T3 minus T2. So for this one, heat is rejected, CV at constant volume as well. That is T4 minus T1. Is that taken? T4 minus T1. So in that case, I can call this one Q1 minus Q2 over Q2 for Otto cycle. Then I will have my Q1, which is what I explained now, that is CV, that's T3 minus T2. Then I have CV T3 minus T2 minus CV, that's T4 minus T1, all over CV, which is T3 minus T2. Is that clear? Now for Otto cycle, the efficiency, if you split it, this one will be CV T3 minus T2 over CV, that's T3 minus T2 minus CV T4 minus T1, then CV, then we have T3 minus T2. So automatically we are going to have 1 minus CV, we cancel out, then we have T4 minus T1 over T3 minus T2. Is that taken? This is the efficiency, one of the formula for efficiency for Otto cycle. As we advance, we'll still derive more formulas to calculate efficiency of Otto cycle. Now let's go back to the processes that we have. Okay, for process 1 to 2. Process 1 to 2. What is really happening in that process? Process 1 to 2, we have which is adiabatic compression. That's what we have in process 1 to 2. Is that taken? And don't forget the formula that governs adiabatic, it is PV gamma. Is that taken? So for process 1 to 2, we have P1 V1 raised to gamma is equals to P2 V2 raised to gamma. Is that taken? So here I can say that P1, is that taken, over P2, like I bring this one to the other side, then I have V2 over V1, then all raised to gamma. But you know, I told you that compression ratio is V1 over V2. Is that taken? So V1 over V2 is equals to compression ratio V1 over V2 is equals to R. Let me do that, meaning that we're going to reverse this. Then this one is going to be P2, then P1 over P1, P2 over P1 is equals to V1 over V2 raised to gamma. Is that taken? That is adiabatic constant. This is it. The gamma is the adiabatic constant, so which is equals to R raised to gamma. Is that taken? Don't forget this formula. This is one of the most important formula as far as adiabatic process is concerned. Just know that PV is equals to gamma, then you have your P2 over P1 is equals to V1 over V2 raised to gamma, which is equals to R raised to gamma. The R is known as the compression ratio. That is for process 1 to 2 because adiabatic compression was happening over there. So if you look at from process 2 to 3, this is heat added. Is that it occurs at what condition? At constant volume. At constant volume. Because here we are dealing with gas. We are dealing with what? Gas. dealing with gas. So, and you know, from your gas law, you have Boyle's law. Your Boyle's law is PV. Your Charles law is TV. Is that taken? Then you have your general gas equation, PV over T. Is that taken? So here now, process 2 to 3, it is heat addition at constant volume. Heat addition at constant volume. Okay, besides, before we even proceed, there are still more formulas to this process. What's it called? This process 1. This process 1. Let me solve those one there. So we have our, you already know that our P2 over P1 is equals to V1 over V2 raised to gamma. Okay, but what's it called? PV is equals to MRT, where V over M is equals to small letter v. This is capital letter. This is actual volume. This is specific volume. For every volume that you're having in the calculation, it's mostly specific volume. Is that taken? So this is what specific what volume. Then if I have this now, I'm going to have P. Is that taken? Now this over this is equals to RT. You understand now? So here now, which is taken to be specific volume is equals to RT. I hope that is clear. So here, if you make this V the sort of formula, I'll have this to be RT over P. Is that taken? Whereby we cannot have what V1 this. Now let us now come back to this now. Anywhere you see V1, you put RT. Now the next thing we are going to do, let us ignore this R because it is a constant. We can remove it. So we can just have V is equals to what? This. You understand? Now let us now put it into this equation. We still have P2 over P1 is equals to, what is my V1? Now my V1 is now T1 over P1. T1 over P1. Is that taken? Now, what's this one? Divided by V2. I can now say that divided, you know, is going to change to multiplication. That is P2 over what? Over T2 raised to power gamma. Raised to gamma. Is that taken? So I can split this now to be P2 over P1 is equals to T1 over T2 raised to gamma. Hope that is clear. Raised to gamma. Now this one is now, what's this now? P2 over P1 raised to gamma. Hope that is clear. Okay, they are now splitted. So here, you can bring this one to the other side. Is that taken? So by doing that, you are going to have, you know, A multiplied by A raised to power N raised to power M. So I'm going to what? N plus M. You understand? So here I have P2 over P1. Is that taken? Divided by P2 over P1 raised to power gamma is equals to T1 over T2 raised to power gamma. Hope that is clear. So applying your law of indices, so you are going to have P2 over P1 raised to, this one is now what? 1 minus gamma is equals to T1 over T2 raised to power gamma. I hope that is clear. So this is another equation for adiabatic compression. For adiabatic compression, this is another equation. This is another equation. We can still have another equation as well, but better still you write it as P2 over P1 is equals to T1 over T2 raised to power gamma over 1 minus gamma. Is that taken? So still the same thing. That's another equation. Don't forget that. So let us still consider another equation where I substituted for volume. Let me substitute for pressure there. Is that taken? I mean this equation. I mean from this place that I substituted for volume. Let me substitute for pressure. So if I'm to substitute for pressure, I'm going to have P is equals to RT over V. Is that taken? Of which I can ignore this one because it is a constant. Is that taken? It's going to cancel on both sides. So we have P is equals to T over V. That's what we want to substitute now. So normally you should come here. You should use the general distance. You can use anyone actually. You understand now? So here I can now, that's T over C. That's how it's going to be. T over V, sorry. Or better still. So here I can now say that my P1 V1 gamma is equals to P2 V2 gamma. Is that taken? So this one, my P is now, P1 is now the same thing as RT1 over V1. Nice one. Now let me substitute. Same thing goes to P2 is equals to RT2 over V2. So let me substitute. Then I'm going to have P1. Instead of writing P1, I will write all this. I'm going to write all this. Ouch! See it properly. So I'm now substituting for what's it called? P1. So I'm writing this. This one becomes RT1 over V1. Is that taken? Then multiply by V1 gamma is equals to RT2 V2 gamma over V over what? Over V2. You can see this, we cancel this. That's what I'm trying to explain the other time. So here I will finally have T1 according to law of linear, that's gamma minus 1, then T2, then V2 gamma minus 1. This is another equation. We now have what? 3 equations for adiabatic process for compression. The first one, don't forget, we have TV gamma. This is an equation for adiabatic. PV gamma is an equation. Then finally we then have T over P 1 over gamma. It's also an equation. So don't forget any one of this equation. Now the second process for this, what's the second process? The second process is 2 to 3. That is addition of heat at constant volume. Addition of heat at constant volume, which we call isochoric. Process 2 to 3. Process 2 to 3. Isochoric. For isochoric, it simply means that CV, it is added at constant volume. Is that taken? So in that case, yes, we will have P over T is equals to constant. So we are going to have P2 over T2 is equals to P3 over T3. You understand now? So, but because the reason why we're having that is simply because Normally it's supposed to be PV over T is equals to 2, 2, 2, 3, 3, 3. But V2 is equals to V3. From here, you can see volume of 2 is the same thing as what? As 3. That's the reason. So since that occurs, this one will cancel out. Then we have what? This. That's this one we have like this. So we can now make what's it called? P2 the subject, or P3, whichever case. If we are to make P3 the subject, or T3, let us make T3 the subject. We are going to have T3 P2 is equals to P3 T2. Without taking, then I'll have T3 is equals to P3 T2 over P2. You understand now? So whichever case it is, but don't forget we can get our T